and Andrea from Greg Corrado and Jeffrey. Image annotation is a key problem in machine learning, and as we know, there are tens of thousands of object categories out there in the visual world. So a key challenge is how to scale machine learning algorithms to such a large number of classes. Moving in that direction, we look at the scalable classification problem from a slightly different angle called zero-shot learning. In a standard setting, we are given a labeled data set of images, for example, images of lions and tigers, and we train a classifier to predict the conditional probability of 1 for the correct labels and the conditional probability of 0 for the wrong labels. Once the classifier is trained, at test time we are given new images that we haven't seen during training, so the goal is to generalize to unseen images. Now what we're asking is whether it's possible to generalize to unseen labels. So let's say we train on lions, apples, oranges, tigers, and bears, and we want to generalize to wolves, cougars, and greyhounds. So this is an ill-posed problem because the classifier doesn't know anything about the classes that it hasn't seen during training. So we need some side information, or we need some way to represent new classes to the classifier. One way to do so is one-shot learning, when we are given a few canonical examples for the test classes. And the goal is to learn a very good representation at training time to be able to very fast generalize to these new classes. Another approach is to use supervised attributes. So in this setting, we describe wolf as a mammal, a quadruped, which is white, gray, or black, and it has big pointed ears, and it's not spotted. And we name similar attributes for cougar. And there had been some work on this, but the problem is in a larger scale setting, it's very difficult and tedious to manually annotate these attributes, and sometimes it's even difficult to come up with these distinctive attributes for classes that are very close, for example, subspecies of animals or different types of objects. The approach that we are taking is using an unsupervised embedding of the labels and concepts. So because it's unsupervised, we can work with very many classes, and what it gives us is something like this. So for example, it tells us that wolf is something similar to dog and bear, and cougar is something similar to cat, tiger, female lion, and greyhound is something between orange and lemon. So by using the embedding of labels in a vector space and the notion of semantic similarity in that space, we can generalize to unseen concepts. This approach had become very popular recently. There have been 2 papers SNPs last year that I'll talk about them briefly in the next slides. So here's the basic idea. We have this function S that embeds words and concepts in a semantic space, and hopefully lion, bear, and tiger cluster together, and apple and oranges are close together again. Because it's unsupervised, we can run this on as many labels as we want. So we run this on the training labels as well as the test labels, and we get a joint embedding of all of the labels. Now, at training time, we train a projection of images into that space, this function f. Hopefully, the images of lions map to the embedding of the word lion, and images of tigers map close to the embedding of the word tiger. And now we can apply this function to an image that we haven't seen during training, and this gives us a representation for an image of a cougar. And when we include the embedding for the word cougar, hopefully when we look at the vicinity of the projection of the image, we find the cougar word. Now, there are a few research problems here. One is how to define the semantic embedding of label. Second, how to project images into that space. And we simply use k-nearest neighbor search for label retrieval. For unsupervised label embedding, we use the skip-gram of Tomasz Mikolov and colleagues. The idea is that word with similar context will get mapped to similar vectors in the semantic space. And as a sanity check, we just visualize labels from ImageNet, and we see that images corresponding to different types of bears, different types of clothing, and different musical instruments, for example, cluster nicely in this space. This is a 2D t-SNE visualization of the 500-dimensional vectors corresponding to each label. Now, here is our approach, which is deceptively simple. We call this convex combination of semantic embeddings. We run the probabilistic classifier on the images to get these conditional probabilities, which tell us, for example, how likely this image contains a lion, apple, orange, etc. then what we do is that we simply take a linear combination of the semantic embeddings based on weighted by their conditional probabilities. So for example, this is going to be probability of lion given image times the embedding for the word lion plus probability of the word tiger given image times the embedding of the word tiger, etc. This gives us a point in the middle of the embeddings for all of these training points. So we call this convex combination of semantic embeddings because all of the probabilities sum to 1. Now we do a k-nearest neighbor search with query fx to find the k most relevant labels, and that's essentially the classification. Now you can note that a lot of the conditional probabilities are going to be very close to 0. So it's slightly inefficient to go over all of the embeddings and average all of them. Secondly, when the probabilities are tiny, including the embeddings for those classes will inject some noise into the embedding. So we propose a parameter t, which essentially selects only the top t probabilities. And we average the embeddings only for those top t labels. In the simplest case, when t equals 1, this is going to be the embedding for the most likely class label. So we are going to project images only on the embeddings for training images. Now, one benefit of this algorithm is that it requires no extra training as long as we have a conditional distribution, conditional probability for the class labels, and we have the embedding for the words. And for training images, as long as the conditional probability is close to 1, the embedding will be close to the semantic embedding for the correct label. And the output of f of x is likely to stay on the manifold of labels when top t predictions are close in the semantic space. So this relates our technique to locally linear embedding in the sense that we are averaging only a local neighborhood in the semantic space. Now, what are the alternative models? One approach is to use a regression-based model in which we try to fit the function f to images and their labels. So we try to make the embedding for images close to the embedding for the words. And this is an approach proposed by Socher and colleagues in NIPS last year. One problem with this approach is that if the embeddings are non-uniformly sparse in the semantic space, the scale of the squared error is not a good proxy to actual classification error. So we need to normalize the distance based on the density of the neighborhood of the semantic embeddings. And the approach taken by my colleagues is that they try to learn the embedding using a ranking loss function, which tries to map f of x close to s of y and far from all of the wrong labels. So they use a triplet ranking loss function to essentially map images close to their embeddings and far from the wrong embeddings. And this was this appeared at NIPS last year too. And this is our main baseline. Now we run experiments on ImageNet. It has 21,000 labels. It has 1,000 standard labels for training, and there are 20,000 labels for zero-shot classification. The good thing about ImageNet is that it has classes that are very close in the semantic space. As you can imagine, this convex combination of semantic embeddings can only generalize to classes that are very close together. So if we don't see any images of fruits, at training time we don't have any hope to generalize to fruits. But the good thing about ImageNet is that it has a very fine-grained classification of images. And we run the semantic embedding model on Wikipedia. We generate 500-dimensional word embeddings, and we train the convolutional neural nets of Alex Krzyzewski and colleagues on ImageNet to basically compute these conditional probabilities. Now here is the device model in which the softmax layer, the last layer of the convolutional neural net, is replaced with a linear transformation that gives us f, and then they use a ranking objective to fit the parameters of this transformation, as well as fine-tuning the lower levels of the convolutional net. And here is conse, in which we don't remove the softmax layer, but we simply compute this equation, the linear combination of semantic embeddings, to get f of x. And we can do a head-to-head comparison between these two models because we keep the semantic embedding exactly the same. The embedding vectors are exactly the same. And the core visual model is the same as well. Now for experiments, we use 1,000 labels for training. We use 3 different sets of zero-shot classes. In the first set, will include 1,500 labels that are 1 or 2 tree hops away from the training label in the whole set of 21,000 ImageNet labels. And the second set is images that are up to 3 hops away in the ImageNet hierarchy. And the last set is all of the other labels in ImageNet. As you can imagine, the task becomes more difficult as we get farther from training labels. Now here are results. These results are for the case that training labels are excluded from candidate labels. So in the test set, we know that images don't come from training labels, and we give a hint to the classifier by saying, okay, I'm not going to include the training labels in your retrieval set. Here I'm reporting flat heat at K, which is the average percentage of test images for which the correct label is within the K predicted labels of the classifier. We are going to vary K from 1 to 20. Our first observation is that conse 10 performs better than conse 1 from 1% to 8%. And this is not surprising because the conse 1 model can't capture ambiguity in the prediction of the labels, but conse 10 can average ambiguous labels. The second observation is that conse 10 performs better than conse 1000 by about 2%, and our hypothesis is that this is because of the injected noise by averaging so many different embeddings. And lastly, conse 10 performs better than device by 57 down to 15% for different values of K, so we get a reasonable marginal improvement over the previous data. Now here are the results for 3-hop data set. As you can imagine, the numbers become smaller, and here is the results for all of the ImageNet. The task is very difficult, so the numbers are relatively small. And the second task is when we include training labels in the candidate set. So the classifier has to figure out which labels are training labels and which labels are test labels. But somehow, we've given training labels differently than the test labels to the classifier. Classifier didn't see test labels as training at all. And as you can imagine, all of the results get much worse. And at the first prediction, for example, all of the models tend to predict training labels. So they have a bias toward predicting training labels. The ordering changes a little bit, but still conse 10 performs much better when we increase the number of retrieved labels. Now I'm showing some qualitative results. Here is a stellar sea lion. I don't know the difference between different types of sea lions. So if I see this image, I would probably name all of different types of sea lions. And this is what conse 10 does. So it names all different subspecies of sea lions, and it gets it right. The first column shows the convolutional net predictions, and the 2 last columns are the zero-shot predictions by device and constant. Here's another example. Both device and constant get the golden hamster right. And here are some more results. The top one is labeled as a dress, and the bottom one is labeled as a flightless bird. And here are some failure cases. For example, in the top case, it's a farm machine, but we sort of predicted things that make a lot of sense. For example, blue vehicle, truck, tracked vehicle, and complex does a good job too. And at the bottom, you see a picture of a llama. And we predicted domestic llama, for example. One natural question is why conse performs than device on zero-shot learning? Conse didn't have any training, but device was trained to predict correct labels. First, I want to note that conse actually performs worse than device when it's tested on a training set. And device was only trained for those training labels, so necessarily doesn't generalize well to test labels, right? But one point here is that maybe the device model is overfitting to training labels in the sense that because the mapping is unrestricted, it can project images anywhere in the semantic space, and it doesn't respect the manifold of the labels. Whereas in the conse model, the projection is much more restricted, and the labels have to stay sort of on the manifold. So this more restriction gives us better generalization power and less overfitting. In conclusion, I presented conse, the deterministic way to embed images in a semantic space using probabilistic predictions of a classifier. So whatever classifier that we have, we can use this model with that, as well as a semantic embedding that gives us a linear behavior in the semantic space that we want. And our experiments suggest that this model performs well for zero-shot learning compared to regression-based algorithms. Right? Maybe this is like it. Thank you.
So I have the impression that implicitly your loss function is actually taxonomic loss function, and maybe it would be the better measure to figure out how far you are from correct answer rather than to look on the zero on the current loss function, and I think then you could observe even further improvement.
Yeah, that's a good point. So here we only presented results for hit at k, which is not a very great performance measure because of the way labels in ImageNet are designed. For example, a wheeled vehicle might be a farm machine as well as a tractor. In the paper, we have results using a hierarchical error function, but for the talk, I kept it simple and only focused on hit at k. But in the paper, you can see results with a hierarchical loss function that measures how far away from the correct label we are in the ImageNet hierarchy.
So when you feed a picture of the Eiffel Tower at night to an ImageNet classifier, you get tower and electric toothbrush as the two highest ones. But of course, tower and electric toothbrush are not semantically related from Wikipedia, so they would get rejected. So what do you do? I mean, is it a general, because you're learning a document space, but that doesn't have much to do with visual similarity. It has some, but not a lot.
Yeah, that's a great point. So here we're sort of assuming that visual similarity correlates with text similarity. And what you're pointing out is that maybe word similarity based on Wikipedia is not a good proxy to visual similarity. And I agree with that, but for many classes that might be the case, for example, for animals, fruits, etc. So we get good results by ignoring the fact that visual similarity might not be exactly the same as word similarity, but I agree that in future work we can probably rely on, for example, the confusion matrix from a classifier to get a better sense of visual similarity. The good thing about the word embedding model is that it's completely unsupervised and we can train it on Wikipedia, so it's not clear what other source we have for coming up with a better notion of visual similarity, but I agree with that.
All right, let's thank Mohammed again. So we have a 25 minutes break.